Hello students, Professor Nugent here. With this video, we continue our discussion to time series data and serial correlation. We're going to focus on time series basics in this video. We'll discuss notation. We're going to define lags, first differences, and growth rates, as well as the first log difference approximation to growth rates. And we're going to discuss autocorrelation, also known as serial correlation. Let's begin with notation. Let's define yt as the value of y in period t, and let our data set be a set of observations on y1 through yt when there are t observations on the time series variable y. So we may have monthly observations from 1960 to 1999, where 1960 Jan is t equals 1, all right, and 1999 December, that would be your final t. Okay, we're only going to consider consecutive and evenly spaced observations, so we're not going to consider the cases where we have missing and unevenly spaced data. That would introduce technical complications. Alright folks, so this is the notation. Let's just give one more example. If we were considering, monthly data, then, and our monthly data were, for example, non-farm payroll, and that were y, then yt equals 1 would be non-farm payroll for January of 1960. Then y2 would be non-farm payroll for February of 1960, and so on and so forth. Okay, let's talk about lags, first differences, and growth rates. The first lag of a time series yt is yt minus 1. That is the yt minus 1 is the previous observation. All right. Its jth lag is yt minus j. So if we're thinking about a time series and we have yt, let's go like this, and let yt be 1990, then yt minus 1 would be 1989, for example. Okay, so this is the lagged observation, this is the previous observation. We can also talk about the lead observation, yt plus 1, which would be 1991. The first difference of a series is delta yt, and this is the change between periods t minus 1 and t. So delta yt is equal to yt minus 1. The first difference of the logarithm of yt is delta ln of yt, which is ln of yt minus ln of yt minus 1. And this gives us the approximation to the percentage change. Well, the percentage change of a time series yt between periods t minus 1 and t is approximately 100 times delta natural log of yt, where the approximation is most accurate when the percentage change is small. When the percentage change gets big, then the approximation is not very good anymore. Let's look at an example. Thinking about gross domestic product, this is the total value of goods and services produced in the United States within a given year. And we're thinking about real gross domestic product in billions of 2009 dollars, so this has been corrected for or controlled for inflation. Gross domestic product in the fourth quarter of 2016 was $16 trillion, $851 billion. Gross domestic product in the fourth quarter of 2017 was $16 trillion, $903 billion. The percentage change in gross domestic product between 2016 quarter 4 and 2017 quarter 1 is 100 times new minus old divided by old, which is 0.31 percentage points, 0.31%. The percentage change in gross domestic product 2012 quarter 1 to 2012 quarter 2 at an annual rate is approximately 4 times 0.31%, which is 1.23% per year. So what is this saying? Well, if gross domestic product increases by 0.31% each quarter in a year, and there are 4 of them, so if output continues to increase at the same rate over the next 4 quarters, then the annual rate comes out to be about 1.23%. Now I want to point out that this formula, multiplying the rate of change by 4 to get the annual rate, is an approximation. And this approximation only works when the percentage change, when the quarterly percentage change is small. The way to go from a quarterly rate to an annualized rate more accurately would be 1 plus r to the 4, where r is the quarterly rate. This will give you the annual rate. So in this case, r is equal to 0.00031. Using the logarithmic approximation to percentage changes, using the same rule we have up here in the second to last bullet, we can do 4 times 100, so that we have percentage change 4 times 100 times the change in the log, so log of 16,903 minus log of 16,851, and that gives us 1.232%. So you can see that the log approximation to percentage changes is pretty good. Here we have a table of GDP and its rate of change. GDP in the United States in the last quarter of 2016 and 2017. In the second column we have GDP, in the third column we have log of GDP. Third column, growth rate of GDP at an annual rate, so we have 400 times the change in log of GDP. And in this last column we have the first lag of the GDP growth rate. Do note that the quarterly rate of GDP growth is the first difference of the logarithm. This is converted into percentage points at an annual rate by multiplying by 400. The first lag is its value in the previous quarter, and in this table we have rounded all entries to the nearest decimal. So this is a introduction to notation and percentage changes, lags, first differences. Stay tuned to the next video. We will discuss autocorrelation and serial correlation.